Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to talk about how to draw the phasor diagram for an AC voltage source here, sinusoidally varying voltage source, hooked to an LRC circuit, a circuit that's got an inductor, a resistor, and a capacitor. All right, so before we talk about the phasor diagram for the entire circuit, it's necessary to go back. We need to understand what the phasor diagrams look like for resistors, capacitors, and inductors individually. So I kind of highlighted this. If you don't know what this is, go back and watch my videos about AC circuits hooked to each of these individually, but I've got kind of an overview of it right here. All right, so the phasor diagram for a resistor, remember that the voltage, I did the voltage is in blue, is in phase with the current. So here's the angle omega t. The voltage phasor and the current phasor are in phase. In this picture, I drew the voltage shorter. Again, remember, voltage and current are completely separate things. It doesn't even make sense to compare them. So, it doesn't make sense to say 10 amps is more than 6 volts or something, but I had to draw them different lengths to distinguish between them here. Right? For the capacitor, remember that the current led the voltage. If you go back and watch my video about the capacitor, the current leads the voltage for a capacitor, and for an inductor, the current lags the voltage. All right, so these are going to be important facts when we try to draw in phasor diagram for the entire circuit here. All right. Couple more important things. Resistors have a resistance, we'll just say R. Remember that the capacitor and the inductor, they have these properties called reactance. The reactance of the capacitor, it's usually denoted X sub C. It's equal to 1 over omega C, where again the omega is the angular frequency. It'd be 2 pi times the linear frequency. The C is the capacitance. And remember, this quantity has units of ohms. It's effectively a resistance in the circuit. The inductor also has a inductive reactance, right? The reactance is basically the resistance of the inductor in the circuit. So the reactance of the inductor is omega L. Again, that's measured in ohms. So the phasor diagrams in these reactances are going to be very important here when we're trying to draw the phasor diagram for the big picture. So when I'm dealing with phasor diagrams, the first thing I always do is draw the current phasor in. So I'm going to go ahead and do that, and I'm going to do that in red. All right, I like to think of the current phasor as kind of like my anchor in the problem here. There's my current phasor. Now I'm just going to start drawing voltage phasors for the resistor, capacitor, and the inductor. All right, so the resistor, remember, is in phase. I'm going to try to offset that a tiny little bit so we can see both. So there is my voltage phasor for the resistor. I'm going to go ahead and label that maybe V sub R. Now let's do the capacitor. So with the capacitor, remember that the current led the voltage, or another way to say that is the voltage lags the current. So when we draw the voltage phasor for the capacitor, it's going to be behind the current phasor. So that might look something like this. There's my voltage for the capacitor. Now I went ahead and drew that shorter than the resistor. That's going to depend on the relative, what these values are. So I'm just going to, it doesn't matter for now. I'm going to make kind of assumptions about which one's larger for the purposes of getting the picture drawn. Now I'm going to go ahead and draw the voltage for the inductor. Now again, which voltage is the largest? That's going to depend on conditions. I got to kind of assume 1 here for the sake of example. So I'm going to assume that the inductor's voltage here is higher than the capacitor's voltage. Now, cool thing about phasor diagrams, we just treat them like vectors because they are. That's what a phasor is. It's a rotating vector. So notice here these. I can actually add these together, right? And they would add to a single vector, which would be kind of up and left. And that vector is going to be this minus this. So I'm going to go ahead and do that. I'm going to go ahead and change that to, I'm going to get rid of this one, shorten this one. This vector now is equal to the voltage across the inductor minus the voltage across the capacitor. As simple as that. I'm going to get rid of this line here. See why in a minute. All right, now what I'm going to do is I'm going to move this vector to here because that's how vectors add. They're added tip to tail. So I'm going to take this vector and just move it right to here. And now I can draw the vector sum. So there is the net voltage, which is equal to the input voltage. So the angle omega t here is going to be this angle right here in the problem. However, you'll notice we've got another angle here in the interior here. That's an important angle. Oops, I'm going to give that a name. I'm going to call that phi. All right, so now this is equal to the voltage across the resistor. This one is the difference between these two. So let me label these. This one's equal to V sub R. Whoops, I'm going to label those in blue because they're voltages. All right, so this one's equal to V sub R. That's this blue one. This one's equal to V sub L minus V sub C. And then this is the net, which is equal to the input voltage. The omega t angle would be from here to the input voltage. Now, I don't need this anymore. Need a little room anyway. Remember from Ohm's law, each of these voltages can be written, with an IR type of term. So the V sub R is equal to IR. The V sub L is equal to IX. The V sub C is equal to IX as well, but it's IX sub C. This one's IX sub L. This one's IX sub C. The input voltage squared is equal to V sub R squared plus this leg squared, V sub L, V sub L minus V sub C squared. That's Pythagorean theorem on this triangle. So the input voltage can be written as the square root of IR squared plus, this can be written IX sub L minus IX sub C squared. Now, the I, you have an I squared here. Effectively, you're going to have an I squared here. I squared here. This can be factored out. And when we take I and factor it out, and then square root it, let's see, we get the input voltage is equal to I. Then we're left with this quantity square root of R squared plus X sub L minus X sub C squared. Now, when you think about Ohm's law, V equals I R, basically. This entire term has units of ohms. This entire term is called impedance. It's basically the overall or total or net resistance of the circuit, all things considered, the resistor, the inductor, and the capacitor. The important thing to realize, though, is that the impedance is frequency dependent, right? The R doesn't depend on frequency, but these do. Remember, the X sub L, looking right over here, is omega L. The X sub C is 1 over omega C. So the impedance of the circuit is frequency dependent. Most books use the letter Z to represent impedance. So when you apply Ohm's law to the entire circuit, it looks like this. Voltage equals I times Z, where the Z you get from here, square root of R squared plus X sub L minus X sub C squared. Another important thing to point out, that the impedance here is a minimum when these are equal to one another. So there's a frequency that's pretty easy to find. If you set these equal to one another, you can calculate a frequency, and that's what's called the resonance frequency of the circuit. All right, another important thing here. You notice that there's an angle between the current and the input voltage. That angle is very important for calculating power, and I think I'll mention why in another video. But for an AC circuit, right, power is current times voltage times the cosine of the angle between the current phasor and the voltage phasor. So that's this angle right here. And again, I'll talk probably a little later about why this is. A quick mechanical analog would be this. If you imagine an object kind of moving back and forth like this, if you apply a force when it's moving to the right, the amplitude of motion will increase. Whenever your force is applied in the direction of motion, the amplitude of motion will increase, increase, increase. If you apply the force when the velocity is this way, you'll decrease the amplitude of motion. So basically what we're saying is that in order for the amplitude to grow, the force has to be in the direction of motion. And again, I'll make another video describing that later. I just wanted to make a quick description of it. In a similar sense, for effective power transmission, the power transmission is a maximum when the voltage is in line with the current, or in other words, when this phase angle is 0. Now, the phase angle isn't always 0. When it's not 0, we need to know what it is. It's pretty easy to calculate from this right triangle. We would calculate it by tangent of the angle phi equals opposite over adjacent. Now, remember that this is an I x sub L minus I x sub C, and this is an IR, and the i's will just cancel. We're going to end up with x sub L minus x sub C over x sub R, and again, that was an L. That's a C, that's an R. Now, the circuit that I drew, because of the way I chose, I had to decide one of them was bigger. This would be called an inductive type of circuit, and the circuit I drew, the x sub L was bigger than the x sub C. But when you start these problems and you calculate these values, if the reactance of the capacitor is larger, it means that this vector is going to be down here and to the right. Your picture would look basically like this, and then you'd have an x sub C minus an x sub L here. Anyway, that's not really that important. I mean, it's important that you get it right, but whether you put x sub L minus x sub C here in kind of general isn't that important. You're going to tell from your picture. If the V sub L is larger, this will be an x sub L minus x sub C. If the VC is larger, this will be down here like this, and this will be an XC minus XL. And you're always going to have just an R in the bottom. I put X sub R here. That actually is just R, the resistance. Resistors don't have a reactance to them, so this is basically the resistance of the inductor, resistance of the capacitor, resistance of the circuit. Alright, I think that's probably enough for this video. I hope this demonstrates how to draw the phasor diagram for an LRC circuit. I'll go ahead and make some examples, and have a great day.